Rajeshwari MJ. She pursued her BE in Electrical and Electronics at the People's Education Society College of Engineering, Mandya. She pursued her MTech in VLSI Design and Embedded Systems at the Sri Jagadguru Balagangadharanta Institute of Technology, Bangalore. Her personal skills lie in good verbal and written communication skills. Her areas of interest lie in OOPS with C++, renewable energy sources, HVDC transmission, digital relays, automotive electronics, advances in VLSI design. She has also had papers presented at the national level, such as the Innovative Architecture for SoC Multi-Core Hybrid Processor, presented at the RNSIT, Bangalore.
Welcome to UGC lecture series of BSc Physics Honours. Today we are dealing with the subject electronic devices. In this session we are going to concentrate on a topic called bipolar junction transistor. So, some of the topics that we are going to cover in this session on bipolar junction transistors are characteristics of common emitter and common collector configurations. In the previous session we already spoke about common base configuration, and now we are continuing this characteristics, that is common emitter and common collector configuration, that we are going to cover in this session, and also current gains, that is alpha, beta and gamma and relationship between them, that we are going to study, and also lastly that we are going to study about load line analysis of transistors. So, firstly we start with common emitter configuration. This is one of the type of common emitter configuration, is one of the type of the transistor configuration, same as that what we discussed in the previous session about the base configuration. In emitter configuration also the emitter is common for both input and output signal, and also the emitter is very closest, and also we can say it as the emitter is grounded in this type of configuration. So, these are the factors that we need to remember when we are going to talk about the common emitter configuration. So, that is common emitter is common or reference to both input and output terminals, and also emitter is usually the terminal closest to or at ground potential. And also the almost amplifier, the design is using convection of common emitter is due to the high gain for current and voltage, because common emitter configuration, whenever we are going to use a common emitter type of configuration in a transistor, it will have high gain of current and voltage, and also the amplification will be very efficient in this type of configuration. And also there are two set of characteristics that is necessary to know about the behavior of this common emitter configuration, that is one is input characteristics and another one is output characteristics. Input characteristics comes to base terminal and output characteristics come to the collector terminal. First we start with the proper biasing, after that we move on to the characteristic study. So, how we are going to bias for a NPN transistor, that for a common emitter configuration. So, NPN transistor we know it is like this, NPN will be the three layers of n type, p type and n type materials, and also here the emitter is common in the sense this is the emitter terminal where it is common for both input and as well as the output, and this emitter terminal is grounded here. This shows the common emitter configuration, that is we can say in an active region. So, active region, why I am mentioning is here the active region, the common emitter will perfectly behave as an amplifier, and is most of the application that wherever that we are going to use for power or voltage or current amplification, that the configuration of a transistor will be used as common emitter only. So, this current convention and with the symbol of transistor will be also represent like this. With the help of transistor symbol, the emitter will be grounded here, and the current is flowing from base to emitter, and from collector to emitter the base current is flowing here. This is the NPN transistor, that is why not pointing to the emitter current is not pointing to. And similarly we can observe for a PNP transistor configuration, where we can see here the PNP transistor is also having a emitter terminal which is common for both input and output, and the current directions in the PNP transistor, it is quite opposite to the NPN transistor, we can observe this is the emitter current, it is moving downward, but here it is moving upward. Similarly, it is opposite for base current also, the collector current also. This can also be represented with the help of symbol like this, where we can see pointing inwards, the emitter current is pointing inwards and the collector current is moving in this direction and the base current is in this direction. Here also we can say that emitter current, by applying a Kirchhoff law, we can say that the emitter current is a sum of collector current and base current. So, next we move on to the input characteristics. So, for studying the proper behavior of common emitter configuration, we need to study the input characteristics. So, the input characteristics is can be studied with by plotting input current across the input voltage, that is input current is IB here and input current is input current is IB and input voltage is base to emitter voltage. We can plot it in x and y axis respectively. Here IB is microamps because IB is too small as we compare for a IC. So, base current is very small for emitter configuration, and that is why it is represented as it is measured as microamps and compared to collector current. And also IB will follow when IB will be appear when the VBE crosses 0.7 volts, when VB is greater than 0.7 volts for silicon material, if we use as a semiconductor material, or if it is germanium semiconductor material, if it is 0.3 VBE, when IB can be appeared for a 0.3 VBE. So, here if we say the silicon as a semiconductor material, we can observe after 0.7 volts when the VB is greater than 0.7 volt, we can observe the current IB current. And also we can say before this value IB is very low, or we can say there is no IB, and also base emitter junction is forward biased in this mode. And also when increasing the VCE, we can say when increasing the VCE values, that is the output voltage values, that is connected to emitter voltage value, output voltage value, if we increase will reduce the IB for different values. We can say this is for 1 volt it is higher, IB value is very high, but when we increase it to 10 volts it is become lower here, and when it is again increased to 20 volts again it is lower. So, IB value will lower as we increase the output voltage, that is collected to emitter voltage. This is what we studied from the input characteristics of one common emitter NPN transistor. So, now we move on to the output characteristics. This is output characteristics will be formed by plotting the graph across along the y and x axis using the output current and output voltage, keeping a input current constant. For different range of input currents, we need to plot a graph of output current and output voltage. Output current is our collector current, that is measured in milliamps, and output voltage is collected to emitter voltage. And here also we observe the 3 regions, that is cutoff region, active region and saturation region. And for small VCE, very small VCE, IC increases linearly with increasing of VCE. For small VCE we can observe here it is increasing, IC is increasing linearly, that is what we can say. And also when VCE is much greater than VSAT, this is a portion that where we can say is VCE is very much greater than VCSAT. IC not totally depends on VCE, we can say here, and IC will be constant at this point, and when VCE is constant for IC. So, IC will be constant when VCE greater than VCSAT. There is a saturation value will be there for output voltage. When it is crosses the IC, the current collector current will remains constant for different even though we raise the VCE. So, this is what we can observe, the IC will be remains constant here, the IC value will be remains constant for varying a VCE. So, also IB, that what we are taken different values is always measured in microamps and is very small to compare to IC which is measured in milliamps. So, small increase in IB causes a big increase in IC that we can observe from output characteristics. So, IB in microamps, which is from 0 we taken as of initial value. After that, if we increase to 10 microamps, there is a big difference we can observe here for a collector current, which is a big difference when we increase a small, when the small increment in the base current. And also on IB is equal to 0, we can say that current, so IB is equal to 0 also we can found some value of current, that collector current. That current is called as ICEO, that is collector to emitter when base is open. This is we can observe here when IB is equal to 0, there is some current flow, small amount of current flow, that is called as ICO, that is the collector to emitter current when base is open, and this region is called as cutoff region. And also noticing the value when IC is equal to 0, there is still some value of current flow will be there. So, IC is equal to 0 also, there will be some value of current is flowing here, that is also we can observe. When IC is equal to 0 also we can say some value of current is flown here, we can observe from the output characteristics. Now, look into the some of the equations, that is we already know and discussed in the base configuration, common base configuration, and also the transistor operation. That is for the very first equation that we know is IC is equal to alpha IE plus ICBE is what the equation that we found, and this substituting here IE value we know IE is equal to the sum of base current and collector current. Substituting this in this equation will become IC is equal to alpha into IC plus IB. So, this is a value that we have, this is the equation that we how we found in the sense that alpha is equal to IC by IE is what from common base we got, but here in the cutoff region also we are finding some small amount of current. So, we added this here, that is the ICBO that is added here, that is a small current, and output current that is common collected to base when emitter is open. And now, the collector current is now become when we apply IE value, IE is equal to IC plus IB, this we substituted here. So, this is the equation we got. After rearranging this equation, this again it will become like this, that is IC is equal to alpha into IB divided by 1 minus alpha plus ICBO divided by 1 minus alpha. This is what the equation that we get after rearranging, that is multiplying this and after rearranging for and taking the common IC. So, finally, our collector current is equal to ICEO, that is common collector to emitter current when the base is open. So, that is equal to collector current, and the when that is equal to collector current is when IB is equal to 0, when base current is equal to 0 microamps, this is what that the collector current is equal to ICO. So, here we substitute IB is equal to 0, so this entire term will be 0. So, remaining term this only will be represent the IC. So, IC is equal to ICO, that is equal to ICBO divided by 1 minus alpha is what the expression that we get for collector current. So, some of the things that we need to remember from the output characteristics is which is having 3 regions, one is active region, saturation region and cutoff region. What exactly happens in this 3 different region? So, comes with active region, it is base and emitter junction is forward biased in this type, and also common collector and base junction is reverse biased in the active region, and it can be employed for voltage, current and power amplification. So, perfectly it always have an amplifier because we can amplify current, voltage and power. And in the saturation region, base to emitter and collector to base junction is forward bias. Thus, the value of IB and IC is too big. In saturation, IB value and IC value will be too big here, and also the value of VCE, that is collector to emitter voltage is small, so small, and also suitable region when the transistor as a logic switch. So, in saturation region this type of configuration can be used used as a logic switch, and also not and avoid this region when the transistor as an amplifier. So, when we are going to use a transistor as an amplifier, we need to avoid this region. So, if we want to use the transistor as a logic gate or logic switch, we can use it in as a when the transistor working in a saturation region. And this is the configuration that when we find that when cutoff region is there, when cutoff region is there, we know that when IB is equal to 0 and the current is flowing in this current direction, and ICE is what the collector current that we found with the base open, that is the collector to emitter current with the base open is what the current flowing when IB is equal to 0. This can be also shown in this fashion where base open collector to emitter current is what the ICO represent, and the direction of current flow is from collector to emitter. So, region below IB is equal to 0 microamps is what we said as a cutoff region, and this has to be avoided if an undistorted output signal is required. So, if we do not want to get any distortion in output, we need to avoid this cutoff region, that is below the IB, below the base current is equal to 0 microamps, that region, that is cutoff region. Below this we need to avoid if we expect that output should not contain the distortion. And also in cutoff region, the base to emitter junction and collector to base junction is reverse biased, and also IB is 0 and IC here it is having a small value, that is IT is not 0 here, and during this condition we will say IC is equal to ICO, where this current flow when base to emitter is reverse bias, that is what base to emitter is reverse bias, this ICO is flows when a base collector to, that is called as collector to emitter current when base is open. So, next we need to know about beta or amplification factor with the help of common emitter configurations. So, in DC mode the levels of IC, that is collector current and base current, are related by quantity called beta, that is defined as beta DC, that is equal to the ratio of collector current to base current, and where here base current and collector current are determined at a particular operating point on the characteristics. And if we say for a device with a 200, if a value of beta will be 200, the collector current is 200 times the magnitude of the base current. So, if we say that 200 is a beta value, that implies that the collector current is 200 times the base current value. So, this is what exactly the beta value means. So, it reminds that it is 200, the collector current is always 200 times more than the base current. So, on specification sheets beta DC is usually included as HFE, this is a hybrid parameter that we discuss in later sections, and we remember that this is HFE, where in a data sheet it is represent that beta DC as HFE. And also for AC, the beta will be represented as beta AC is equal to delta IC divided by delta IB. For VC is equal to constant, where the VC has to be kept constant, and also beta AC is also called as common emitter forward current amplification factor. So, next we move on to another type of configuration, that is common collector configuration. So, it is also called as emitter follower. So, common collector configuration is also called as emitter follower. It is called a common emitter configuration since both the signal source and the load share the collector terminal as a common connection point. So, as we know from previously studied two type of configuration, the collector is common for both source and load, and also the output voltage is obtained at emitter terminal. So, the collector is common here in the sense the output is obtained from the emitter terminal. The input characteristics of common collector configuration is similar with common emitter configuration. So, input is similar with the emitter configuration. So, common collector will be having input characteristics that is similar to the emitter configuration, and also common collector circuit configuration is provided with the load resistor connected from emitter to ground. So, that emitter to ground, that load resistance is connected in common collector, and also it is used primarily for impedance matching. This type of common collector configuration is mainly used, the application is for impedance matching. Why we are going to use it as a impedance matching? In the sense it is having high input impedance and low output impedance. Because it is having high input impedance and low output impedance, we can use this circuit as an impedance matching. So, the notation and symbol for common collector configuration for PNPN and PNP transistor, it is like this. For PNP, that where we can observe the collector is common for both input and output. And this is the emitter current and it is flowing from emitter to collector, and base current is this, and this is a bias voltage that we can give from base and also from emitter, and is a majority carrier that is flowing from emitter to collector. And this is where we can say for PNP transistor, this is a collector is common, this is how the current is flowing from emitter to collector. And also in NPN also same with a different current direction, which is having three different currents, that is emitter, base and collector. With the emitter is common, we have both, it is common for input and output, and it is flowing from collector to emitter here, that is the collector current is flowing from upward towards emitter here, from collector to emitter. And this can also be written like this, where we can say this B is NPN transistor that is not pointing in. So, it is moving outwards to the emitter. So, from collector to emitter is what the flow of current here. So, for output characters, so we can skip the input characteristics, because for common collector the input characteristics is similar to common emitter configuration. So, we are studying only output characteristics here. For common collector configuration, the output characteristics is plotted is like this, that is emitter current versus the collector to emitter voltage for a range of values of base current. And here also we can observe it is having three regions, one is saturation, another is active, and a third one is cutoff regions, which is plotted here. The VCE is where we can observe it starts from 0 itself, we can see the current can be observed, the emitter current is increased with this VCE is equal to 0 is what the difference that we can observe from other two configuration. And also when IB is equal to 0, there is a small current, that is IE, that is emitter current is not 0 when the IB is equal to 0. There is some value of emitter current will be there when IB is equal to 0. And also for small change in base current, there will be large change in the emitter current. And also when VC as VC increases after saturation, that is when it reaches a maximum value, when the emitter current reaches maximum value, after it retains a constant value for if we vary the VCE for further values also, the IB will be the emitter current will be constant for different values of base current. This is what we can observe for a common collector output characteristics. So, from common collector output characteristics we come up with another factor, that is gamma. It is a current gain in common collector configuration, and it is a ratio of emitter current, that is output current, to the base current, input current. So, gamma is represented by the ratio of emitter current to base current, and it is also called as emitter efficiency, that how much current is injected from the emitter to base after recombination of minority charge carriers in base is what the value of gamma that is given, that is what is called as emitter efficiency. So, due to the recombination, how much that current will flow due to the injection from the emitter to base after recombination of a minority charge carrier. In between the PN and NPN junction, the minority charge carrier flow will be there due to the injection from base emitter to base. So, that minority charge carrier efficiency will be found with the help of gamma, and also its value will always as high compared to alpha and beta, that what we discussed previously, that is amplification factor beta, and also the current gain factor of common base configuration. So, the gamma will be always high compared to alpha and beta. So, finally, we can have the relationship between the analysis relationship between alpha, beta and gamma. So, previously we studied about alpha in the last session. So, now we know the beta and gamma value also. So, we combine all three and make a relationship between alpha, beta and gamma now. In the case when we know that IE is equal to it is the sum of collector current and the base current, and also from this equation we can say that IC is equal to beta into IB. We can substitute this value here, so that we can make this equation this equation and rewritten like this by substitute IC value here. So, this equation will become IE is equal to beta plus 1 into IB. So, keep this equation aside. So, next case 2, that is where we know two values, that is alpha and beta. Alpha is equal to the ratio of collector to emitter, and beta is equal to ratio of collector to base. So, from this alpha and beta we will get IE value and IB value. So, IE value and IB value we got this, and now we are going to substitute these two in equation 1. that is IE value and IB value. So, IE value is substituted here and IB value is substituted here. So, by substituting these two here we will get a alpha and beta relationship like this. By substituting IE and IB value in equation 1. So, for gamma we know that it is the ratio of emitter to base current. So, and also we know this equation, that is emitter is current is equal to 1 plus beta of IB. So, here the IB value can be written with the relation of gamma. So, IB is equal to gamma divided by IE is what that we get. IB is equal to IE divided by gamma. So, IE divided by gamma is what we written in place of IB value. So, we got a beta and gamma in one expression. So, we are rearranging this, we can have a relationship between the beta and gamma. So, this is how the beta, alpha and gamma can be have a different relationship by substituting each other. So, some of the limits of operations of a transistor that should be known for us for the transistor operation, for knowing that the transistor has to be operated in a better way. So, some of the limits that we need to know, that are many BJT transistor used as an amplifier. Thus, it is important to notice some of the limits of operation, that is at least 3 maximum values mentioned, that is in a data sheet. That is what the 3 maximum values are. Maximum power dissipation. So, this has to be mentioned in data sheet, that is the limit for a transistor to operate. So, maximum power dissipation at collector will be PC max or PD, it is represented, and also maximum collector to emitter voltage, that is VC max. This is also named as VCO and also sometimes called as VB or CVC of CEO. And also another maximum value that we need to know is maximum collector current, IC max. So, these are the 3 maximum values that we need to know for better operation, or that limits of operation for a transistor. There are few rules that need to be followed for BJT transistor used as an amplifier. The rules are, when we are going to use a transistor as an amplifier, these rules has to be followed. So, the transistor need to be operate in active region always. So, from all the characteristics that we studied for different common emitter, common base or common collector, the active region is where we can say it will always operate in as an amplifier. So, transistor has to be operated in active region whenever we need to use a transistor as an amplifier, and also the collector current should be less than IC max. So, this is the limit of operation. So, collector current is always less than IC max, and also the power dissipation, that is always less than the maximum power dissipation at collector. So, at collector the power dissipation should be less than that what they mentioned in the data sheet, that is the maximum power dissipation at the collector. Next, we move on to the operating point and the concept of load line here. The particular condition of the circuit where with some definite values of voltage and current can define the region or the point of operation of the circuit. So, some certain voltage and current value will give a certain point of operation. So, that point of operation is called Q point, where we can say the Q point is a point, it is a still point or unvarying point with certain current and voltage values. And also, since most of the time transistors are used for amplification, the region should be so selected that at the output we obtain a faithful and an amplified representation of the input signal. So, the faithful in the sense that whatever the input the signal is given, the faithful amplification in the sense the complete input signal has to be appeared as an amplified. There should not be any distortion in amplification. So, the complete input signal has to be amplified in the output signal, that is what is called as faithful amplification. So, this is where that we can say for different values of current and voltage, if we consider this is a region of operation, this is called as a Q point. If we consider like that similar values, output characteristics, we will get different values here, and if we join all these values, which is gives the load line. So, the load line is a graphical function used to find the device currents and voltages when the device is described by its characteristics curves. So, this is what the load line, which will going to give the characteristics curves, and even when the characteristic curves of the device are not available, the load line solves the purpose as it gives the locus of all such points on the curve where the device can be operated and a corresponding output can be obtained. So, even the output characteristics is not given. With the help of load line analysis only we can study the characteristics of a transistor. That is what the benefit of a load line. So, load line is given by this is it is a locus of all the current and voltage values which gives a load line. So, using the load line analysis we can know the characteristics of a transistor. In this session we studied about two types of configuration, that is emitter configuration and also collector configuration. So, we come up with the relationship between alpha, gamma and beta, and also finally we end up with the load line analysis. So, some of the questions of this session are: explain the common emitter configuration, derive the relation between alpha, beta and gamma, mention some of the limits of operation in BJT. This ends the session. Thank you.